In this video, we're going to be looking at a counter, a digital counter that uses JK flip-flops, and we have it hooked up on a circuit board that's attached to an analog digital trainer. The trainers make it a lot simpler to test devices, and they have a lot going on. They're nice to use, but if you don't have one of these, that's okay too, because we'll show you some tricks how you can build some circuits that take the place of the trainer. What we're doing with the counter is we're going to clock the JK flip-flops, and we'll eventually start with the reading of all zeros. We have 4 flip-flops, so that's 2 packages because they're dual flip-flops, 2 in each package. So we'll start with 0, 0, 0, 0 in binary, and we'll eventually, as we clock the first flip-flop, it'll ripple through the counter and bring us to a count where they're maxed out at 1, 1, 1, 1. So if that were hex, it would be the letter F because we have 4 bits. And let's go ahead and get started. So we have a little bit of a close-up on the trainer. We'll go ahead and fire power up here, and you can see a couple of lights lit up on the side here that shows us that our power supplies are active. And we already have the 5 volts wired in to a small circuit board where we actually built the circuit. They give us a lot of room to work on the main board, but this circuit was designed elsewhere, so we just went ahead and wired it into the trainer, and we'll show you the operation. So right now it initially started at 0, 0, 0, 0. All right, so it could start anywhere. When you first fire it up, it pretty much is random as to where it starts, but we have the JKs on each one of these things tied high. The set and the resets are all tied high on these 2 flip-flop ICs, and there's 2 flip-flops in each package. So there's 2 flip-flops in this first one, 2 flip-flops in the second one. We're using the part number 74LS76. So that's our JK flip-flop part number that we're using, TTL chips. And of course we have our power and ground. These chips, by the way, are 16-pin ICs. They have a few extra pins because of the JK inputs and the sets and resets and so forth. We have a 16-pin chip that we're working with today. The outputs, the Q, are directly connected to the LEDs that we're going to be looking at. When they're off, like they are now, it's a 0. When they're on, it's going to symbolize a 1. So I have a pulse switch, which again is my clock, and it's debounced, so when I go ahead and pulse it, you'll see that's our first light that lights up. So that signifies the 1's place. So we put the number 1 in because we pulsed it 1 time. It's a counter. Every time I click the button, it'll count in binary. So now the next one is going to go to the number 2, because the first one was 1, the second light is 2. So now we went from 1 to 2, flip it again. Now the 1 lit up as well as the 2, so we have the binary number 3. Another pulse shifts over to the 4, and the 1 and the 2 being off gives us the number 4. I add 1 to 4, you have 5. The 2 should light up next, so I have a 2 and a 4, so I have 6. And now all 3 are 1, it's 1, 2, 4, so that's the number 7. Now when I flip it again, I should come up to my more significant digit, which is the 8. And there I have my binary 8, which is 0008, or 0001, I should say. And now we just go ahead and keep adding numbers. So from 8, I add 1, I have 9. 10, 11, 12, 13, 14, and now when I max it out, they're all lit, 15. This is a buffer circuit that we're going to show you how you can manufacture these things yourself without having to have an analog digital trainer. To light the LEDs off of the high level, we have to keep the current very minimal because the totem pole design of the IC allows for more of a sinking of current rather than a sourcing. So on the high, you get a source of current that's really very low. On these ICs, I think it has to be below 0.4 milliamps. So that's pretty small. So what we're going to do, we're building a buffer circuit. So that's what we have drawn out here. You can see a transistor. We're using a 2N3904 transistor in our circuit. I'll show you in just a second. And we're also using a 10K ohm resistor. So the LED would light up by sending a high from the IC in through the 10K resistor, biasing the transistor on, and it switches it on and lights up the LED that's in the collector circuit. So the LED is connected to a current limiting resistor of about 220 ohms. That's between there and 5 volts. So see, we have a high volt, a 5 volt coming in, and it's going to go through the resistor that limits the current, then it'll light up the LED and then go through the transistor switch. And the actual IC still has a lot of resistance to its output, so it's not going to have to put out too much current. A little hard to see, but it's just a transistor, the resistor for input, which is right here, and then the LED with the current limiting resistor going to the 5 volts. So backing off a little bit, let's see what happens again. So we have our same system where we're still stuck with the debouncing problem. We'd have to make a debounce switch, and that would be our next step. But for right now, this is going to be the 1s in our count, and then we'll go back up to the 2s, the 4s, and the 8s on the trainer. So this is just showing 1 of 4 that you would have to make in order to buffer these LEDs. So when I go ahead and clock it, that 1 lights up. It used to be up top here, but now it's being buffered down here on the other circuit board. And then it'll work just like it did before. When I clock it again, that one goes out and the 2's lights up. Now we have both of them, so that's a 1 and a 2, a 3. We go to the 4, and then now I should have the 5 come up, which is my buffered LED. 6 is 2 and the 4. The 7 is all 3 of those least significant digits, and then I go up to my 8's number, and 9, 10, 11, 12, 13, 14, and all of them 15. Next, we're going to show how we can make a debounced switch. So again, if we don't have an analog digital trainer, we can go ahead and get a 74 LS00 NAND gate, and with this NAND gate we can go ahead and wire it like we're showing in the diagram, where we can use it to be a debounced circuit, and that'll be able to debounce our clock so that we can go through and work our counter. Otherwise, if we didn't have this, there would be just a lot of erratic operation. So what I have to do is I have to ground between the 2 outputs over here. So let me go ahead, and right now we have 0s on our display. We have all the LEDs now at the top being used to display. So if I go ahead and go from one point to the other, you see we lit up the 1. I go from, again, back to that first point and back again to the second. We lit up the 2, and I keep alternating between these 2 contacts, and we're using a debounced latch in order to give us the clock signal that's going to reliably go through our counters possibilities all the way from all 0s to all 1s, where we have the number 15. So let me do this. And of course, instead of just putting a wire back and forth, it's much better to actually get a switch on there that you could toggle. And there we are. So we're up to the count there. Full count. Okay, and then we should reset. There we go. There may be a slight bit of erratic operation when you're using the debounced switch the way I am, just pushing a wire in and out. It probably would be a lot better to use a toggle switch. But in any case, we saw how we could not go through the expense of buying one of these analog digital trainers and instead just make the circuitry needed for buffers for the LEDs, and then also for the debound switch for the clock signal. So, there's always a way around things.